This recording is for Primary Math 4. We're in the challenging word problems. I'll be working pages 4 through 9, which is the practice questions, and then a couple out of the challenging section. We're beginning with some basic number theory. We want to make sure we understand numbers really well. We start by being given the numbers 5, 7, 8, and 0. And we want to find the smallest 4-digit number and the largest 4-digit number, or greatest, that can be formed using these 4 digits. They give us a hint. No number can begin with a 0. If I had the number 0, 5, 7, 8, that's actually a 3-digit number. We don't count the leading 0. Doesn't count as a digit in a number like this. So the smallest number we can possibly make would begin with the 5,000, and then it would be 078. The greatest number we could make, if you start with the biggest number of 8,000 and go 7,050, those numbers are just going to go in descending order from greatest to smallest, and that'll make the greatest number possible. Now there's an extension at the bottom of this that wants to know what happens if you want to know the smallest odd number. Well, an odd number, have you thought about this in a while? An odd number has to end in an odd number. If it ends in an even number, it's even. A number that ends in an odd number is, in fact, an odd number. And so this question, the smallest odd number, is going to end in the 7. It has to end in either a 5 or a 7, but I want the 5 to be in front. All right, two options are I could end it in a 5, which would make the 7 in front, or I could end in a 7 and make the 5 in front. If I'm going for the smallest, then this one, of course, is not a good answer. I don't want it to be 7,000. I want it to be 5,000. So in this case, the smallest number is going to be 5,087. The second extension that they offer us is the greatest odd number. Okay, again, same idea. For the greatest odd number, I could have it end in a 5, or I could have it end in a 7. In this case, both of them are going to start with an 8,000, but in this, in the top one, if I end in a 5, I can have a 705, but if I end in a 7, I can only have a 507. So the greatest odd number is not going to be this one. I want to have the 5 in the ones place, so I can use the 7 in the hundreds place. A little bit of thinking, certainly some guess and check can go on. It's fine to play with the numbers a little bit and figure out how to make it work. Number 2 is the same exact kind of problem, only now they've graduated us up to using 5 digits. And in the problem, we're trying to find the smallest 5-digit number, and then the extension asks us to find the smallest and greatest even and odd numbers. So let's think about the smallest and the greatest, and then we'll extend it and think about the smallest and greatest in even and odd. The smallest number is going to begin with the smallest possible value, and then the numbers are going to go up as slowly as possible. 20,479 is as small as you can possibly go. The greatest number starts with the biggest possible number and gets smaller as slowly as possible. Now, so that would be the answer to part A and part B. But then the extension, when it asks the smallest and greatest 5-digit even and odd number, if I want to do the smallest even and the smallest odd, notice that the very smallest number possible is an odd number. So I have actually already found that. It's 20,479. If I want to find the smallest even number, then my last number is either going to be 2 or 0 or 4. And the smallest number I can get really needs to have a 2 in front. And I don't want to have a 4 or 7 or 9 next. I want it to be in the 20,000 range. but I have to have one of those numbers at the end, so that'll be the 4. And so the smallest I can go and make it an even number is 20,794. Then if I do the opposite side, and I'm trying to find the greatest of the numbers, and I want to find the greatest even and the greatest odd, I have kind of the other one this way, because the greatest possible number of all possible numbers is an even number. So I have already found that one. And I just have yet to find the greatest odd number possibly. An odd number is either going to end in a 7 or a 9. I'm looking for the biggest possible number. I sure want to use a 9 in the 10,000 place. So I'm not going to use the 9 in the ones place. I want to save the biggest number to use that in the 10,000 place. So I can't use the 7 next, but I could use the 4. 94,207 is going to be the greatest odd number that I could possibly use. And then one more time, just to make sure we have really caught on to the game and the plan, we have the digits 3 and 4 and 7 and 0. We're going to use them to find the greatest odd 4-digit number for part A. And part B is going to be finding the smallest even 4-digit number. So, if it's an odd number, I know for sure that I have to either have the 3 or the 7 in back for my 4 digits. Because I want it to be as large as possible, I want to save that 7 to be used as high as possible. So to make an odd number, I'm going to put the 3 in back. And then the rest of my numbers are going to go largest to smallest. 7,403 is the greatest odd 4-digit number I can come up with. For my even numbers, if I want it to be the smallest, again, I have the choice. Is it going to be a 0 or a 4 in the back? Well, in this case, I want to have the 0 to be the biggest number possible, so the entire number stays small. It's a little counterintuitive. You have to think about it a while. So the smallest number I could possibly come up with here would start with 3,000, and then I would use the 4, I'm sorry, not the 4, if I use the 400, and 70, that'd be an option, but look what happens. If I use the 4 here and the 0 in the hundredths place, that's even a smaller number. So it's kind of funny, when you want the smallest even number, you have to use the largest even number at the end, because I want to save the 0 in the hundredths place and not a 4 in the hundredths place. Okay, again, play around with it. It's easy to get it kind of backwards and confused. Writing down all the possible ones that are even is not a bad idea to figure out which one works. Number 4 is just practice in rounding. Rounding is a simple concept, but it somehow becomes hard in a lot of our minds. And so what I want you to remember is, if you're rounding to the nearest 100, the only number you have to pay attention to is the number in the tens place. The instructions on this problem are to round to the hundredths place. So because of that, all I have to do is to watch or look at the tens place. If the tens place is higher than 5 or higher, I should say, then it's going to round up. So the 23,000, the 7 is high enough to make the 400 into a 500. In part B, the 4 is not high enough to change the 7, so it's going to remain a 700. In part C, the 5 is high enough to change. This time it changes the 0 into a 100. And in part D, the 5 is high enough to change the 400 into a 500. So that is rounding to the nearest 100. Number 5, we're rounding to the nearest 1,000. And so we're going to look only at the hundreds place to decide what to do. The rest of the number doesn't matter at all. In part A, the 900 means I'm going to round up 1,000, and my answer will be 19,000. In part B, the 4 means the 120,000 is not changed. Part C, the 5 means the 486,000 rounds to become 487,000. And in part D, the 900 means the 199 rounds up to 200,000. Wherever you're rounding at, you're going to look at the next place and the next place only to decide if it rounds up or doesn't round up. Number 6. The question is, what is the common factor of 39 and 54 that is greater than 1? To find a common factor, I like to use what I was always called a factor tree. 39 is 3 times 13, and already I'm down to prime numbers. So I have to stop. I can't factor any further. The only thing I can factor for this is 1 times 3 and 1 times 13. 54 I can factor. If it's an even number, I always start with 2, and 2 is a prime number, so that part is finished. 27 is 3 times 9. Again, I have a prime number on one part of it, and the 9 factors down to 3 times 3. This is an easy way to find prime factors of any numbers. And the question they're asking me is, what is the common factor besides 1? Well, the only number that these have in common is that both of them have a 3. 54 does not have 13 as a factor, and 39 doesn't have a 2 as a factor, nor are there multiple 3s that we could take out. And so the answer is simply that 3 is a common factor of those numbers. Number 7 asks us this question: what is the difference between, and then it tells us what we're finding the difference between, the sum of the first 2 multiples of 9 and the third multiple of 9. Now when you see the word difference, I hope that you think and that your mind goes to the fact that that is a subtraction problem. And so what am I going to subtract? Well, the sum of the first 2 multiples of 9, and the first 2 multiples of 9 are 9 and 18. The sum of those, sum means add, so the sum of those is 27. It's the difference between that number, which is 27, and what else? The third multiple of 6. Well, let's think about 6. 6 and 12 and 18. 18 is the third multiple of 6. The difference between those two numbers is 9. The math is not hard. They just want to know, can we learn to read through a lot of words and come up with a mathematical interpretation of the question. When you read this, make sure you separate out. It asks you, what is the difference between, and then it tells you the 2 things you're going to find the difference between. The first one starts with the sum of the first 2 multiples of 9, and then there's the word and then there's the next one, the third multiple of 6. Learn to read those in a way that you can pull that apart and know what it's asking you to solve. Number 8, what is the sum of, here we go, again, this one we're finding the sum of the first 3 multiples of 4 and the first 4 multiples of 3. We're trying to find the sum of all of these numbers. Now, when you add numbers together, if possible, it's nice to put them in some sort of a grouping that makes sense. When I see these, I see a whole lot of 12s around. If I'm adding all these numbers together, I see, just by looking at it, I looked at it and I'm like, well, there are 4 12s and 6. 4 12s is 48, and 6 more than that is 54. So that's the answer to the problem. That's the sum of the first 3 multiples of 4 and the first 4 multiples of 3. It sounds more confusing than it is by a long shot. Number 9, it wants us to find the smallest whole number that is divisible by 4 and 8 and 11. Now let's talk about terms for just a minute. If a number is divisible by 11, what does that mean? Well, that means if I take 22 and I divide it by 11, it equals 2, and the remainder is 0. Having a 0 remainder means it's divisible by 11. 66 divided by 11 is 6 with a remainder of 0. So 66 is divisible by 11, but 67 is not divisible by 11, because that gives us 6 with a remainder of 1. So if it's divisible by something, it means it's a multiple. So really what we're asking is, what is the smallest multiple of those 3 numbers? Okay, and you might remember least common multiple is the skill that we're working on here. They don't call it that exactly. They make you kind of figure that out and discern it a little bit. But if I have the numbers 4, and by the way, 4 is factored as 2 times 2, and 8, which if I factor it all the way down to prime numbers is 8 as 2 times 2 times 2, and 11 is a prime number, so it can't be factored. The least common multiple will be the combination of these numbers that includes the smallest combination that includes every one of them. So I can't just have 2 2's for the 4, I have to have another 2 in there for the 8. And I have to have an 11 in there. Notice I could say this is 4 times 22. This number is 8 times 11. And of course 11 times 8, if I want to say it backwards just to make it fit the pattern. This number is going to be divisible by every one of these numbers because it is a multiple of each of them, and that number is 88. That's the smallest number that I can come up with that all of those numbers will go into evenly because it's the least common multiple, and that's what we mean. A multiple is what we mean when we say it's divisible by another number. Number 10. P is a number. When I multiply P times 7, and then I add 4 to the answer, the result, what I get, is the 13th multiple of 3. And we're trying to find, our task is to find what is the value of P. That's what we want to know. Well, basically, this is a work backwards problem. Now, you might start getting a little panicky, feeling like you're doing Algebra 1 with your young child, but you're not. We're setting up the idea of algebra and an equation and working backwards and undoing things around the variable, but that's not what we're doing yet. So just teach them this with a straight face and let them learn it without any concern. 13th multiple of 3, how do we find that? Well, you might think about the second multiple of 3. Is 6. And by the way, do you notice that's 2 times 3? The fourth multiple of 3 is 12, which is 3 times 4. So when we're looking for a 13th multiple of 3, all we have to do is realize that we're looking for 13 times 3 and 39. Now, for one problem, you could have counted by 3's 13 times and known that just as fast, but overall, it's good to know that the 13th multiple of a number is 13 times that number, and that you can find the number of multiple simply by multiplication. That is the basic definition of multiplication. So if I do all of that, let me just erase this and come back at it with a clean page. If I do all of that, I'm going to end up at 39. Now let's just kind of say we start at a spot and we take, that's P, and we're going to multiply it by 7 and we get an answer. And then we're going to add 4 and we're going to get 39. Well, if we're moving backwards along our trail to go the other direction, before I added 4, I had to have been at 35, because when I added 4, I got 39. So to go backwards, I'm basically undoing. Instead of adding 4, I've got to subtract 4. And then the same thing here. If I multiplied by 7 to get 35, if I'm going to undo that, I'm going to divide by 7, and that means I'm going to start out with a 5. And you can certainly check that and make sure 5 times 7 is 35. And if I add 4 to it, I get 39. So I followed the path the problem suggested. I multiplied by 7 and I added 4, and I definitely ended up with 39, which is exactly what I wanted to end up with. And so that means that I started my whole problem, I started with P is equal to 5. Number 11. This year, it says Isaac's age is between 30 and 60, and it is a multiple of 6. What multiples of 6 are between 30 and 60? Well, there's 36, 42, 48, and 54. One of these numbers is his age this year. It goes on to tell us that next year his age will be a multiple of 7. Well, you've probably counted birthdays long enough to know if this year you're 36, next year you'll be 37. A 42-year-old becomes 43, a 48-year-old becomes 49, and a 54-year-old becomes 55. The question is, I want this year's age to be a multiple of 6, which it is, and I want next year's age to be a multiple of 7. This is my winning pair. 49 is 7 times 7, and 48 is 6 times 8. So what I have is a multiple of 6 this year and a multiple of 7 next year. The question is, how old is he now? And so somewhere we want to write the answer. He is 48 years old. 48 isn't enough. It might be 48 days or 48 decades. We need to know 48 years old. Go ahead and write a units with your answer every time. Make sure it's clear. Number 12. I'm thinking of a number from 40 to 60. When it's divided by 5, it leaves a remainder of 3. Again, let's stop and think about remainders again. We talked about this a minute ago. If I start with the number 5 and I divide it by 5, I get the answer of 1 with a remainder of 0. What do I have to do to get a remainder of 3? Well, if I keep on going, eventually, right, I'm going to get a remainder of 3. If I'm dividing by 5, what I have to do is increase my number by 3 above a multiple of 5 to get a remainder of 3. Let's take this a step further. If I have 8 divided by 5, I get 1 with a remainder of 3. What's the next number that I have that's a remainder of 3? Well, that would be 13. Because my multiple is 10, if I add 3 to my multiple, that's going to give me 2 remainder of 3. My next multiple of 5 is 15, so 18 divided by 5 also gives me a remainder of 3. We're looking and thinking about the remainder theory, theories about remainders, and it has surprising applications in math, actually. The remainder theorem is very helpful, and it also shows up on SAT tests. So beginning to think at this level about a remainder theorem is a really good idea. So we're thinking about a number between 40 and 60. When it's divided by 5, it leaves a remainder of 3. So between these two numbers, 43 would work, or 48, 53 or 58. 63 is too big, so that one won't work. But then we have more information. When it's divided by 4, it leaves a remainder of 1. So if I'm going to divide it by 4 and it leaves a remainder of 1, I must have a multiple of 4 and add 1 to it. That's how I get a remainder of 1. So what are my multiples of 4 in this group? Well, 40 is a multiple of 4, so 41. Maybe I should make a list of multiples to keep it straight. There's 40, 44, and 48. It was easy to count by 5s, a little harder to count by 4s. 52, and 56, and 60. So if these are my multiples of 4, and I want to have a remainder of 1, then it could be 41, 45, 49, 53, 57. Now 60 is actually out of bounds. 61 doesn't work. So here's the thing. I'm thinking of a number between 40 and 60. When divided by 5, it leaves a remainder of 3. That means it's one of these numbers. When divided by 4, it leaves a remainder of 1. It's one of these numbers. What number am I looking at? It would have to be the number 53. Now in this case, my answer is a number. I don't need units. They ask me, what is the number? And I'll tell them the number is 53. Because of the way the assignments go, I'm going to go ahead and put the challenging problems on the same recording because this is all week 1. So on page 9, the challenging word problems portion, Mrs. Holmes has a monthly expense of $38,100, and that's rounded to the nearest 100. So the question is, what is the greatest and the smallest possible value that her expenses are if they round to 38,100? Here's what we remember. If it's not going to round, we're only looking at, if we're rounding to the hundreds place, we're only looking at the tens place. If I want it to round to stay at 1 and not go up, the highest this number can be is 4. It doesn't matter if this is a 9, it's still going to round down to a 1. I'm sorry, it's going to still leave the 1 where it is and not round anything. It's just going to stay that way. So the biggest number I could possibly start with and still round down to a 1 is if I have a 4 here and that 9 is as big as I can go without making this 4 in the tens place into a 5. So 38,149 rounds to 38,100. On the other hand, I could have 38,000, and in these next digits, maybe I started with a 0 that I rounded up because I had a 5, and this number can be as small as it needs to be. That 5 already means I'm going to round that 0 up to a 1 in the hundreds place. So what we find is that if I round to 38,100, it has to be any number equal to or smaller than 38,149 and equal to or larger than 38,050. Every number within this region is going to round to be 38,100, including, of course, the boundary points. Last problem for this recording, number 2. We have 12 sandwiches that are going to be arranged on a plate, or plates, and we need to know that each plate is going to have the same number of sandwiches. What are the possible number of plates needed? Well, in a sense, what this is a factoring problem. What I know is that I can have factors of 12 like this. These are the only way that 12 divides evenly. So I could have one plate and have 12 sandwiches, or I could have 2 plates and each of them would have 6 sandwiches, or I could have 3 plates and each of them would have 4 sandwiches. But because the numbers are different, the sandwiches and the plates are different, I could also have 4 plates, and each of my plate has 3 sandwiches, or I could have 6 plates on which I only can fit 2 sandwiches each, or I could have 12 plates with 1 sandwich each. So, what are the possible numbers of plates that you need? You would need to have either 1 plate or 2 plates, 3 plates or 4 plates, 6 plates or 12 plates. Any of those amounts of plates you can use and put sandwiches on them evenly. You cannot take 12 sandwiches onto 5 plates evenly. It leaves a remainder, back to the idea of what is divisible.